Hey, welcome back to Calc 2. In this video lecture, we're going to take a look at the material in section 11.10 on Taylor and Maclaurin series. This is the first part of two video lectures that we'll spend in section 11.10. So the goal of this first part is to show you, or define rather, what a Taylor and a Maclaurin series are for a given function. And then I want to compute several examples. Okay, so we skipped over section 11.9 just to sort of save us a little bit of time as we're making it through this virtual semester. But I do want to write, or I borrowed the following theorem from it. So let's take a look at what it says, and I'll kind of show you just say real quickly how I plan on using this. Okay, so if you have some power series, we looked at what that means last time, and it has some radius of convergence. We looked at what that means last time, so here it's written out. It's power series centered at A. The theorem says that that power series function on its interval of convergence is differentiable. It's differentiable, well, maybe not on the interval of convergence, but at least on the open interval. Okay, so A minus R to A plus R. And you can term by term differentiate it. The derivative is found just by pretending it's a polynomial. It's a polynomial. A power series is a polynomial that never stops. So if you can differentiate a polynomial, you can differentiate a power series. You just take, well, the derivative of C0 is 0. Derivative of C1 times x minus a is C1. The derivative of C2 times x minus a squared is 2C2, and so on. It's just the power rule. Likewise, you can integrate a power series. You have to add a constant of integration, and then you add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. And the radius of convergence for those differentiated or integrated power series will be the same. It won't change R. Okay, you have to still check the endpoints. So that's kind of just a real quick summary of what section 11.9 was about. That a power series function on its interval of convergence, possibly minus the endpoints, is differentiable and integrable, and you can differentiate and integrate them term by term. All right, so I'll show you how I'm going to use that. We started our whole work. I tried to motivate, it seems like it was a long time ago, but I tried to motivate the entire chapter 11 by showing you this sequence of polynomials that the more and more terms I added to it, the closer and closer it approximated the sine function. You remember that? You can go back and watch the video again if you can't remember it. It was when we first started. It was the very first video of chapter 11, section 11.1, part 1, where I had these polynomials. They had kind of weird coefficients. I didn't say anything about where they came from, but the more and more terms I added to those polynomials, the better and better I got a graph that was approximating the sine function. All right, those polynomials were just partial sums of a power series, and moreover, they were partial sums of one of these things I want to tell you about, a Taylor series, Maclaurin series. So here's the idea. You have some function. Maybe it's sine of x, and you'd like to write that function down as a power series because most of the time, because you want to truncate it somewhere and use some polynomial to approximate it. But let's just say we want the whole series for a second. So I want some function, and I want it to be a power series. So what do I don't know? I don't know the coefficients. Yeah, so if you hand me a function like sine of x, and you hand me a center, like x equals, or a equals 0, or whatever you want, then I need to find these numbers, C0, C1, C2, an infinite set of numbers that makes that power series converge to your function value, f of x. Well, using the theorem above, we can start doing some differentiation. F prime of x, if we term by term differentiate in the summation notation, look what I'm doing. I'm taking my exponent, bringing it down, and lowering it by 1. If you want to do that out in longhand, I wrote the derivative here. The derivative of the constant is 0. The derivative of this linear term, because the derivative of x minus a is 1, you just get C1, 2 came down, and so on. Pause the video and differentiate that thing yourself. Make sure that what I'm writing makes sense to you, that's just the power rule. It's the very first rule of differentiation you ever learned. The second derivative, okay, well, differentiate again. When you take the second derivative, C1's going to die because its derivative is 0, and you'll end up with this number 2C2, and then this 2 will come down and multiply by 3, and notice instead of writing 6, I'm kind of trying to build a pattern, so I'm just going to leave it as 3 times 2. Right? This 4 gets multiplied by that 3. I'm not going to write 12. I'm going to write 4 times 3. Let's do one more. And this one, I've left some room so I can slow down and write it with you. So if we write it in the summation notation, I've got the sum from 0 to infinity. I've already got this n and this n minus 1. I got to multiply that by n minus 2. Does that look familiar? That pattern that's growing, n times n minus 1 times n minus 2. I hope it looks familiar. I'd have Cn, and finally I'd have x minus a. Now I've lowered the exponent 3 times, so I'd have an n minus 3. In longhand over here, what would be true? Well, the 2c2 term, its derivative is 0. So the first non-zero term I'm going to get here is 3 times 2 times c3 times 1 plus 4 times 3 times 2 c4 times x minus a to the first, plus I'm out of room, but you can take some time and write the next term. So I'm just term by term differentiating those things. Okay, and now to turn around and kind of solve for the c's, here's the kind of cool part. Notice that as we do this, C0, C1, not always just it, but 2C2, 2 times 3 times C3, those are the only terms with no x minus a in them as we go down. So if you plug x equal a into this series, all of the terms with factors of x minus a in them are going to go away. They're all going to go away. So we can end up solving those equations for the c's. That's what I want to know, right? So what do I mean by that? Let me see if I can leave this in view as I start trying to write it down. So if I plug in x equal a into this expression that I'm underlining, every term in the double underline part is 0. So what's left? C0. That's all I'm writing down here. And I can solve that for C0. It means C0 is f of a. So we just learned the 0th coefficient. It's the function value. All right, what if we plug x equal a into this sum? Well, all of the double underline terms are gone because they have x minus a in them. So we just end up with C1. Solve it for C1. Good, C1 is the first derivative. Great. All the terms with x minus a and the second derivative are gone. We're left with 2C2. So when you plug a into the second derivative, you get 2C2, and that means that C2 is 2 factorial. Or sorry, a C2 is f double prime of a over 2. I left myself one. If we plug in x equals a into the third derivative, all that's left is 3 times 2 times c3. So if we write that, 3 times 2 times c3, we can solve that for c3. It's the third derivative at the center over 3 times 2. And a nicer way to write that, it's the third derivative at the center over 3 factorial. Look above, the pattern even works. It's the second derivative over 2 factorial. This is the first derivative over 1 factorial. Sorry, I'm kind of squeezing these in. This one, let me write it over here. This is just the function over, it even works, 0 factorial, because 0 factorial is equal to 1. So if we kind of dot, repeat that, this is the kind of punchline that I want to get at. The nth coefficient in this power series that I want to know, it's just the nth derivative of my function f at the center divided by n factorial. All right, so if we arrange for those to be the coefficients, what have we done? We've cooked up a power series that has the same value as our function. It's got the same first derivative as our function. It's got the same second derivative as our function, and so on, right? So such a power series should closely approximate our function, right? We have to answer the question, on what interval would it do that? I mean, we know that it's guaranteed to converge to our function at the center, but hopefully it'll converge on some interval with some positive radius of convergence. So let's get some language under our belt before we move on. What we just constructed is called the Taylor series. The Taylor series for a function centered at A is the infinite series. It's a power series centered at A, and the nth coefficient of it is the expression that we just derived, the nth derivative of f at A, the center, divided by n factorial, all right? This is just sort of some historical notation, but if A is equal to 0, if the center is equal to 0, instead of saying a Taylor series centered at 0, you can also call it a Maclaurin series. And I know we're kind of full of terminology. The only reason I'm bringing that up is because you're going to see it in your book. Your book is going to talk about the Maclaurin series. They won't always say the Taylor series centered at 0. So I need you to know what it means. But in some sense, it's vestigial terms, but I don't mean to be disrespectful to Maclaurin or to Taylor. Their names are both attached to this stuff. They're both English mathematicians. But a Maclaurin series, just make a note of it. It's a special case of a Taylor series. It's when the Taylor series is centered at 0. So in particular, the notation looks a little different, right? We don't write x minus 0, we just write x, and I'm plugging in 0. So the Maclaurin series is f of 0, f prime of 0, x, and so on and so on and so on. All right, let's find one. How do you find a Maclaurin series for a given function? Well, you basically have to understand this pattern. You have to understand, like, what do I get when I plug a 0 into the nth derivative of the function? So this part, let me actually outline it in something that I can keep. This is really the number that you need to compute. It's going to be some function of n, because the rest of that stuff in this formula is static. You're always going to take what's in that red box and divide it by n factorial and multiply it by x to the n if you're finding a Maclaurin series. So let's start off with the function e to the x. I left myself some room. Let me leave that formula right there. So what do I have to do? I have to start taking my function, f of x is e to the x, and I basically have to be able to understand a pattern. I need to be able to write down what the nth derivative of that function is as a function of n and x, so I can then plug in x equals 0 and find out what number I need in that red box. All right, for e to the x, that pattern is pretty quick to establish. The first derivative of e to the x is e to the x. The second derivative of e to the x is e to the x. I've already caught on to the pattern. The third derivative, the fourth derivative, they're all, yeah? So this is your goal in general, is you want to know this formula. And for e to the x, it's easy. The nth derivative of e to the x is e to the x, yeah? So if you plug in the center, a equals 0, the nth derivative of e to the x, evaluated at x equals 0, a equals 0, is, well, e to the 0, it's a 1. So for this particular function, the thing that I need to put in that red box up there for every value of n is the same number. It's a 1. All right? So let's do it. The Maclaurin series for e to the x is the infinite sum. Let me try to keep that red box in view up there. I can't quite keep it all. It's the infinite sum as n goes from 0 to infinity. In the red box, we put a 1. The rest of the formula is static. N factorial times x to the n. And kind of a nicer way to write that might be like this. All right, and let me summarize it in a kind of a nicer way. E to the x, let me give myself a little bit more room. So e to the x, it's Maclaurin series. It's the sum as n goes from 0 to infinity of x to the n over n factorial. If you want to write a few terms out of that, and I highly recommend that you do, it would start off 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Yeah, so that's its Maclaurin series. And then we have to answer the question, what's the radius of convergence and the interval of convergence? I'm just going to refer to keep this video short and not repeat things, because you can go back and look. So look at the section 11.8 video where we talked about power series. This was one of our examples. I believe it was example 3. In that, I hope, I'm not wrong about that. I'm going to give myself a little bit of wiggle room, but this exact series was the example there. And we found that the interval of convergence for this series was minus infinity to infinity. All right. So this Maclaurin series converges to e to the x for every value of x. You take any real number x, you plug it into that series, it's going to converge to e to the x. So this is, if you like, how your calculator sort of really deals with e to the x. It doesn't use the whole series. It probably truncates it somewhere, probably more than x equals 3. But if you wanted me to estimate something like e squared and I didn't have a calculator, well, I could go, well, e squared, x is 2, it's about 1 plus 2 plus 4 over 2 plus 8 over 6. Maybe I'd stop right there. That's probably a pretty decent estimate of it. Yeah? So these partial sums, let me show you them just by kind of highlighting. The 0th partial sum of this thing is just the constant term. There's the first partial sum. It's a linear function that approximates e to the x. The second partial sum, you'd stop at the quadratic term. Sorry, you'd stop at the quadratic term. Third partial sum, stop at the cubic. As you add more and more terms to that polynomial expression, it's going to look like e to the x more and more. Let me show you that graphically. I think I've got this set up to where I don't have to switch stuff around so much. Let me just switch over to Desmos here real quick. I've just plugged that series in. I can't point. I don't have a laser pointer here in Desmos, but if you're looking over on the left in the box 1, I've got e to the x, so it's drawn in red. I hope it looks familiar to you. And then I've got this series that we just derived, x to the n over n factorial. So you can stop the video and look back. That's the Maclaurin series, except here, the upper limit, Desmos can't let me literally take an infinite sum, but I can let it be any number capital N that I want. And then I'm just going to let capital N increase one kind of thing at a time. So when capital N is 0, let me actually, I want to put these things side by side. So let me do this. So I'm thinking about this series. And let me see if this is going to be big enough. Come on. iPad. Sorry, this is frustrating, but I'm also frustrated by making all these videos, and I am not going to stop this and edit it, so you can just tell yourself that I am a crappy video maker. Okay, I'm going to try this one more time. I am trying to not have a fit about this. If you think I sound annoyed, I am highly annoyed. I want to just put these things side by side. You can't see it anyway. So here's our e to the x series. This is stupid. Let's just try to look at the graph. If I move this counter, I'm adding terms one at a time to our series. So right now, this is just the constant function 1. It's the first term in the series when n is 0. If I click n up to 1, okay, that's the first Taylor polynomial approximation of it. So it's drawn in blue. It's the tangent line. If that polynomial, if you can stop the video and go back and look, it's just the polynomial 1 plus x. That's the tangent line. If we add another term, it's going to be 1 plus x squared over 2 factorial. So what do we get? We get a quadratic polynomial. So check that out. That quadratic polynomial, it's got the same value of our function at the point. So f of 0 and the Taylor series of polynomial are the same there. It's got the same tangent slope, and it's got the same concavity. So that's a degree 2 approximation for it. If I wanted to add one more term, I add the cubic term. Now I'm adding the 5th degree term and so on. And you can see that as we get away from the center, those things are diverging. Can you still see the red curve? But as I add more and more terms, these polynomials, look at that. They're approximating the exponential function better and better. So anywhere you can't tell the difference between the blue and red curve, the approximation is extremely accurate. If we zoomed way in on this, we would of course be able to see the difference, but you really have to zoom far in, yeah? So that's what I mean by the radius of convergence is infinity. I've found a sequence of polynomials. Let me switch back to notability. What I was just plotting was I was adding those terms. I wanted to be able to see it all at the same time, but I can't. That first straight line was just this polynomial, 1. And then we looked at the linear one. That was the tangent line. Then we looked at a parabola. That was it had the same second derivative. Then we looked at a cubic term. The more and more terms we add, the closer and closer it gets. And in fact, as you let n go to infinity for any x, that series is going to converge exactly to e to the x. Cool. Let's do a different example. Let's find the Taylor series for e to the x centered at not a Maclaurin series, but let's center it somewhere else. So you have to do the same thing. You have to take a bunch of derivatives. I'm going to keep the video short and say, we already said that the nth derivative of e to the x is itself. Yeah. But now if I want the Taylor series centered at a equals 3, I'm not plugging in 0 for x, I'm plugging in 3. So this time I get e cubed. So everywhere up there, go back if you don't know what I mean by this, in the red box, I have to put the number e cubed. It doesn't depend on n, it's the same for every n. So I can write down the Taylor series referring to that formula. E to the x is the infinite sum, as n goes from 0 to infinity, of e cubed over n factorial. But be careful, you have to put x minus the center to the n. All right? So if you started writing out a few terms of this, when n is 0, you're going to get e cubed over 0 times 0, you're going to get e cubed. And then when n is 1, you're going to get e cubed times x minus 3. And when n is 2, you're going to get e cubed over 2 factorial times x minus 2 squared, and so on. So again, it's a polynomial expression that this thing, I'm going to leave it to you as an exercise. But the interval of convergence for this is also the entire real line. If you apply the ratio test to that series, I hope you'll do it, you'll find out that it converges for all values of x. All right? So if we try to look at a graph of that thing, although I honestly don't know why I'm trying this again, because there. So I have it set up. Let me make this just a little bit bigger, and then we can look. Let's see. So I've got a Taylor series for the natural exponential graph. Good. So same kind of thing. And this time I think, well, I need the slider. So notice this time that my zeroth, I know you might have to squint in. I'm not sure if you can see this, but if you just take the first term only, e cubed of this thing. If you plug in x equals 3, you get e cubed. So that's where the function then agrees with the 0th Taylor polynomial, the approximation where I just take the first one. So this blue line is that constant e cubed, and it's crossing the graph e to the x at 3. So the y values there are e cubed. If I make the slider click up n equals 1, now what I'm looking at is this polynomial, the linear polynomial, e cubed plus e cubed times x minus 3. That's the tangent line. It's always going to be the case that the degree 1 Taylor polynomial, that is chopping it off at the linear term, that's the tangent line, because it's got the same function value and the same slope. If we make the slider go to 2, now it's a parabola. So the first 3 terms are drawn there. And notice that it's approximating very well again, but this time the approximation is all sort of accurate the closer and closer you get to 3. That's the business, that's what the center does. When you pick the center of the Taylor series, you're kind of saying where you want the approximation to be accurate from the very beginning. And then as you, in this case, because the interval of convergence is infinity, the higher and higher you take those powers, you can't tell the difference between my functions anymore because I've let n get really big. You'd have to zoom out in the picture, getting far away from the center. Remember, the center is 3. You have to get far away from the center before the red and blue graphs start looking different from each other. Okay, let's try it again. So this time, the example I want to do is finally, this was the example that motivated chapter 11. So if you're still around, you hung with me through chapter 11, you've been wondering for a couple of weeks, where did Dr. Evans get those polynomials that so closely associated the sine function? Well, I got them by calculating the Maclaurin series for sine. Yeah, so I just kept adding terms one at a time. I was just adding the terms of the Maclaurin series. So that little Desmos animation that I showed you, I had just read ahead into section 11.10 and learned how to do this Maclaurin series for sine. So let's do it here. The derivative pattern for sine is more complicated than it is for e to the x. So let's see if we can't try it. Okay, so let's start by taking some derivatives. When you're doing a Maclaurin series from scratch, like what we're doing right now, or a Taylor series, this is how you start. You start differentiating the given function over and over and over again until you feel like you can write down a formula for the nth derivative in terms of n. Okay, let's see if we can do it. So f of x, the 0th derivative, just put a little counter over here. Actually, let me do that later. So f of x, the 0th derivative is sine x. The first derivative is cosine. The second derivative is minus sine. The third derivative is minus cosine. The fourth derivative is sine. Oh, well then the fifth derivative is going to be cosine again. The sixth derivative is going to be minus sine again. The seventh derivative is going to be minus cosine again. And then the eighth derivative is going to be sine again. So it's just going to be repeating. It's going to be repeating. We only get 4 distinct derivatives. Yeah, every time we go through 4 distinct derivatives, we just repeat sine, cosine, minus cosine, sine, cosine, minus cosine. It's a harder pattern than e to the x, but still, it's not completely impossible to digest. Every 4 terms, you sort of start again. Let's see what these things are going to do at our center. So I'm just going to kind of make a table here. I'm plugging in a equals 0. Okay, let me maybe over here I'll index. We were taking the 0th derivative, the first, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, dot, dot, dot. Okay, when we plug in a equals 0, what do we get? Well, the sine of 0 is 0, but the cosine of it is 1. Sine of it is 0, the cosine of it is 1. I understand that pattern. The coefficients, the things that I have to write in the red box, the things that I have to write in the numerator of that Maclaurin series formula, those numbers go 0, 1, 0, minus 1, 0, 1, 0, minus 1. All right? But that by itself is not all that satisfying, because how do I write that down as a function of n? The zeros, first of all, when coefficients are zeros, those terms get multiplied by 0. They drop out of the sum. And for that matter, I don't really know how to write down something that alternates 0, 1, 0, minus 1, 0, 1, 0, minus 1. I don't know how to do that. I do know how to do 1, minus 1, 1, minus 1, 1, minus 1. We do that with powers of -1. And since we don't need to write the 0 terms anyway, let's just kind of adjust our index, because we can't write, the sum over some of the n's. The n has to start at 0 and click all the way up when we write down that formula. But let's notice something here. Maybe I'll switch to a highlighter so it'll stay. When do we get non-zero terms? Well, we got one when we were on the first derivative, the third derivative, the fifth derivative, the seventh derivative, only the odds. Yeah, when we're on an even derivative, we get zeros. 0th derivative, second, fourth, sixth. So I only want to keep the odd terms. So here's a technique for doing that. How do you only keep odd numbers? Well, the number 1, you can think of it as, say, like 2 times the number 0 plus 1. The number 3, you can think of that as 2 times 1 plus 1. Odd numbers are always 1 more than an even number. That's all I'm trying to say. 5 is 2 times 2 plus 1. 7 is 2 times 3 plus 1. You see the advantage of what I'm doing here? This thing, the multiplier, it's clicking up one at a time. That's what I want my n to be. Yeah, because n, I want it to start at 0. And so I'm abandoning these old n's. I don't like these old n's, 0, 1, 2, 3, because they were skipping 0, 1, 0, minus 1. I want to use this new n, because when the new n is 0, I pick up the first non-zero term. When the new n is 1, I pick up the second non-zero term. And for that matter, the signs work out. If I just make the signs -1 to the n, then it works, right? When n is 0, I get +1. When n is 1, I get -1. When n is 2, I get +1, and so on, right? But what I have to remember is that in the expression, these new n's don't really correspond to the old n's. The old n's are these numbers. So I have to, any place in that formula for the Maclaurin series, there was an old n, I have to kind of remember to replace it with 2n plus 1. It's my new counter. I'm being a little sloppy here. I should have used maybe two different variable names because I'm calling it old n and new n. But I think if you're kind of with me, you can follow what I'm about to write down. The sine of x, what do we put as our coefficients? I'm going to take my new n, letting it go from 0 to infinity. I know I want the signs to alternate like that, but I'm not, that's the number in the red box. But because I'm skip counting now, I'm not going to put n factorial. I'm going to put 2n plus 1 factorial. I only want the odds. And for that matter, on the powers of x, I only want the odds. All right? So that's how we can take care of those zeros dropping out. So if we write this out, if we start with our new counter n equals 0, the first term of this thing is going to be x. And then the signs are going to alternate. The next term is going to be x cubed over 3 factorial. And then we're going to get x to the 5th over 5 factorial, x to the 7th over 7 factorial. And now I can finally tell you, this is where I was getting those polynomials for the sine function. This is where I was getting them. I was just plotting for you on Desmos way back in section 11.1. I was just plotting x and then plotting x minus x cubed plus 3, and then I plotted the first 3 terms, and then I plotted the first 4 terms, and the more and more terms I plotted, the closer and closer it got to the graph. Let's see, I guess I'm in kind of a torturous mood today because I'm going to try to make Desmos play nice again. I can just go back. I saved that way back in our work in section 11.1. So I can just show you here. Here, I guess I called the counter m here, but that the green curve you're looking at is the sine function. Yeah, that's the graph of sine of x. And right now the counter is 0. And so I'm just looking at the first term. So back here in our lecture notes, I'm just plotting x. That's the line x. Red line is x. If I make the counter go up to 1, now I'm plotting the function x minus x cubed over 3 factorial. It's cubic, and it approximates a little better. Here's the first 3. That goes out to the 5th degree polynomial, then the 7th degree polynomial, and then the 9th degree polynomial, the 11th, the 13th, and so on. The higher I make the exponent, the better and better this thing approximates, and for that matter, further and further away from the center. Further and further away from the center. All right? So I'm going to leave it to you as an exercise, or we can do it together in class. Calculate the radius of convergence and the interval of convergence for the sine function. I'll tell you the answer. The answer is the radius of convergence is infinity, and the interval of convergence is minus infinity to infinity. Verify that. Use the ratio test to verify that. It's good practice for you. Okay, let's do one more example. I think this video is getting long. I never watch the clock when I'm making them, but it feels like it's getting long. I'm tired. Sometimes, the algebra involved in finding the formula for the nth derivative is hard. Maybe you're even convinced of that right here, right? This was hard. The pattern was harder to establish than e to the x. Depending on the function, it can be terribly hard. But a lot of times in practice, you don't really care about the whole series for the function. You might just be happy having a few terms, maybe you just want to approximate it with like 3 or 4 terms, like what I was talking about before. If you wanted to estimate the sine of 1, fine, just take this thing and plug 1 in for x. It won't exactly equal the sine of 1, but it'd be pretty good. Just take the first 4 non-zero terms of the Taylor series, the Maclaurin series, centered at 0, and plug in 1 to that. That would give you a darn close approximation to the sine of 1. Yeah. So sometimes that's good enough. I just want to illustrate that you don't have to look for a pattern. If you want the first 4 non-zero terms of some Maclaurin series, Taylor series centered at 0 for a given function, you don't have to differentiate until you get a pattern. You just have to differentiate until you have at least 4 non-zero coefficients. 4 because that's what I asked for. Let's try it. I'm doing a homework problem, by the way. This is number 5 on page 771. I don't feel bad. There's 4 other problems in that block that I'm asking you to do. I'm just including this example so that you have some idea of like, well, what's it asking me to do? Find the first 4 non-zero terms in the Maclaurin series. So, well, it's asking you to do this. Take your function, f of x. That's the 0th derivative, right? It's x times e to the x. Plug in the center, you get 0. So that's not going to give you a non-zero term. I need 4 non-zero terms. I need this number to be different than 0 4 times. So let's try this first derivative then. So f prime of x, well, you got to use the product rule. F prime of x is e to the x plus x times e to the x by the product rule. So f prime of 0 is 1. Good. That's a non-zero term. So we know what to put in the red box for our x to the first factor, right? This is a Maclaurin series, so we're going to expand in terms of x minus 0. Let's take the second derivative. Well, we got to use the exponential rule and then the product rule again. So if we plug in 0 there, what do we get? We get 1 plus 1 plus 0, we get 2. That's not 0. I need to keep doing this until I get a non-zero derivative 4 times. So we've got 2 of them. How about the third derivative? See, I'm not thinking about patterns. I'm just thinking about the derivatives. So the third derivative is e to the x plus e to the x plus e to the x plus x e to the x. You probably can see a pattern here. It's nothing wrong with it, but I don't need to. You plug that in and you end up getting 3. Okay, that's not 0. Fourth derivative, well, it's e to the x plus 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 x e to the x. Plug in 0 to that fourth derivative, and you get 4. That's 4 non-zero numbers. Yeah, so we can write down this function, x e to the x. It's not going to be exactly equal to, but it should be close to, at least on its interval of convergence. We'd have to worry about that in another question. But what can we do? I'm just going to take this first number that was not 0. I have to remember what derivative it went with. It was the first derivative. So I take that first number, 1. I divide it by 1 factorial, and I multiply it by x to the 1. I'm just doing that to show you the pattern. And then I have to take the second number, that was this 2, that went with the second derivative. So I have to take that 2 and divide it by 2 factorial and put it to x squared. Our third answer, 3, goes in the red box over 3 factorial. That's the x cubed term. The fourth answer, 4, has to go over 4 factorial. Yeah, so there's the first 4. And if we simplify this, it looks a little nicer if we just write x plus x squared. 2 factorial is 2. 3 over 3 factorial is also 2. So we get plus x cubed over 2 plus x to the 4th over 3 factorial are 6. All right. So there's the first 4 non-zero terms of the Maclaurin series. First 4 non-zero terms. I'm going to let you do it. I'm not going to do it on Desmos. If you plotted this function, x e to the x, and then you plotted those 4 terms near the center, near x equals 0, those graphs will be very close to each other. They're going to have the same value, the same tangent slope, the same concavity, the same third derivative, and the same fourth derivative. Yeah, so they're very, very close approximation. This thing is sometimes called degree 4 Taylor polynomial. So a polynomial is not an infinite sum, it's a finite sum. So I've cut the Taylor polynomial off at x equals 4, the Taylor series off at n equal 4, so I get a Taylor polynomial. All right, thanks for listening, and I hope to see you in class.